Welcome, everyone, to this explainer on Borsh and Rust fundamentals. I am so incredibly excited for today's topic. Oh, and right off the bat, this session is brought to you by Forge College. Now, if you've been working your way through the Programming with Solana track, and specifically the Exploring Borsh Serialization module, well, you're in the exact right place. Today, we are taking the abstract beauty of Rust concepts and crashing them headfirst into the concrete, totally unyielding reality of Borsh bytes. This is the absolute foundational layer you need before we start writing custom serializers. Okay, let's just dive right into this with a really simple question. Have you ever actually wondered what your perfectly crafted Rust struct looks like when you strip away all that compiler magic? Like when it's stripped of its formatting and just dumped as raw, literal bytes on a disk? It's kind of like looking at the underlying matrix of your code, right? So today, I'm inviting you on an exclusive tour of what I like to call the Borsh Serialization Factory. We're going to see exactly how that transformation happens. So here's the blueprint for today's factory tour. We'll start with a welcome to the factory itself, then compare automated and manual serialization, figure out who actually owns the data, unpack memory layout and padding, talk about future-proofing with version tags, and finally, get you ready for the assembly line.
All right, Section 1, welcome to the Borsh Factory.
Now, if you tuned into our previous lesson on integration considerations for Borsh, you know we discussed some high-level strategies for byte-level stability. Well, today we're applying those strategies to the literal-minded packing machine that is Borsh. So what is it? Basically, Borsh serialization is a process that encodes structured data into a deterministic, compact, little-endian byte sequence. And you know, the absolute keyword here is deterministic. Think of Borsh as this robotic packer on a factory floor. It literally does exactly what you tell it to do with zero ambiguity. It doesn't guess, it just packs. Moving right along to Section 2, automated versus manual serialization. So stepping right onto the factory floor, we essentially have two different ways to pack our crates. On one side, we've got derive macros, specifically BorshSerialize and BorshDeserialize. You can think of this as your automated assembly line. You just tag your struct and boom, the macro does the heavy lifting for you. But on the other side, we have manual implementation. This is much more of an artisan by-hand approach. You're going to use this when you need absolute, complete, low-level control over exactly where every single byte goes. The crucial point to take away here is that the derive macro, that's going to be your routine workhorse. It auto-generates this perfectly consistent, reliable encoding. Plus, it serializes your fields in the exact order you declare them in your code. And let me tell you, that prevents a ton of really subtle, annoying ordering bugs on the assembly line. Oh, and it also automatically uses a 4-byte length prefix, which is an unsigned 32-bit integer, whenever it encounters a collection, like a vector or a string. Honestly, it's incredibly safe and it'll handle about 95% of your daily workload.
Section 3, who owns the data? Let's talk about ownership.
Okay, if Borsh is our super literal packing machine, Rust is essentially the overly strict factory bureaucrat standing right next to it with a clipboard, completely obsessed with ownership. When we unpack or deserialize our crates, we basically have two choices. We can create owned values. This means we actually allocate brand new heap memory to reconstruct our Rust types. It's very safe, sure, but it takes resources. Alternatively, we can use borrowed views. Instead of copying data into new memory, we literally just point a reference at the exact bytes sitting right there in the original input buffer. And that brings us to a highly advanced technique known as zero-copy deserialization. Now, just between you and me, zero-copy is basically an extreme sport for programmers. It is incredibly fast. It's super efficient because you bypass allocating or copying entirely. But it requires incredibly strict lifetime management. We're talking high stakes here. You make one wrong lifetime move and the Rust borrow checker will absolutely end you. So just keep in mind, by default, the derive macros do not do zero copy. They play it safe and reconstruct owned values. All right, Section 4, memory layout and padding. This is a big one. Listen up, because here is the golden rule. Borsh doesn't automatically mirror Rust's in-memory padding. Imagine our literal-minded robot packing a physical box, okay? In memory, Rust often throws in these empty padding bytes so the data aligns perfectly with your computer's CPU architecture. It's exactly like packing peanuts. But Borsh hates packing peanuts. It completely strips away all that platform-dependent fluff and only packs the exact sequence of data bytes you handed to it, nothing else. And because Borsh throws away those packing peanuts, you need to be really careful. because Rust's native standard memory size of command might actually lie to you about your serialized size. I'm serious. Native memory sizes include that invisible padding. So if you try to predict your Borsh payload size using size of, your calculations are going to be completely wrong. You absolutely must calculate your serialized lengths explicitly based on the Borsh encoding rules. So let's look at exactly how common Rust types map to their deterministic shapes on disk. An unsigned 8-bit integer? Simple. That's just 1 byte. Larger integers, like U16, U32, or U64, they take their respective byte counts, and, this is key, they are always packed in little endian order. Now, a Boolean takes up a full 1 byte. It's either a 0 or a 1, not a bit field. And those dynamic types like a string or a vector, they will always start with a 4-byte length prefix, telling Borsh exactly how many elements follow. No hidden padding, no mystery whatsoever, just pure, predictable shapes.
Moving to Section 5, future-proofing with version tags. So we know how Borsh packs the boxes, but how do we label our crates so the factory can still actually read them 10 years from now? Well, we do this by deserializing a versioned enum. It's a 3-step process. Step 1. You read exactly a 1-byte version tag, which is usually a U8 discriminant. Step 2, you match that tag to your specific variant, so say settings version 1 or settings version 2. And step 3, you route your parsing logic to read the exact sequence of bytes expected for that specific version.
Let's look at an example. If we serialize a settings struct that is version 1 with a threshold of 10, the resulting deterministic output is beautifully simple. It's literally just the bytes 1 and 10. The 1 is our version tag, and the 10 is our threshold. It's elegant, it's totally machine-readable, and if we ever decide to make a version 2 with more fields later on, our old systems will still see that 1 and know exactly how to handle the next byte.
All right, so here is your future-proofing checklist for manual enum deserialization. First, guarantee you read exactly 1 byte for the tag. Second, match that tag accurately. Third, always use from little endian bytes to convert the data. And finally, this is absolutely crucial, always return an explicit unsupported version error for any unknown tags. Doing that guarantees your future code can remain beautifully compatible with your old bytes.
And finally, Section 6, ready for the assembly line. Okay, we're wrapping up the tour. If you remember literally nothing else from today, remember these 3 fundamental principles that bridge Rust's rigid rules with Borsh's literal packing. Number 1, Borsh is explicitly little endian and deterministic. Number 2, your Rust ownership strategy completely dictates whether you allocate new memory or play the dangerous but very fast game of zero copy. And number 3, perhaps most importantly, Borsh layout ignores native memory padding entirely. I'll say it again, do not trust size of. So, I'm going to leave you with this final thought to chew on. Borsh is utterly explicit. It writes exactly what you emit. Nothing more, nothing less. Your bytes are your responsibility, so plan them wisely. This foundation prepares you perfectly for our next lesson in the Implementing Borsh with Rust module, where we are actually going to write basic serializers. Thank you so much for joining me on this factory tour. As a reminder, this explainer was brought to you by Forge College. I highly encourage you to go visit forge.college to dive deeper into the subject and discover a whole wealth of other fascinating Web3 related topics. Keep learning, keep experimenting, and I'll see you in the next one.